Science has a very specific way of saying it is wrong. It does not announce it loudly. It does not hold a press conference to admit the textbooks need to be rewritten. Instead, it finds a planet that, according to every model, every simulation, every carefully constructed theory about how solar systems form and evolve, simply should not be there. And then it finds another one, and another, until the weight of impossible worlds accumulates into something that can no longer be explained away as an exception, an anomaly, a quirk of measurement. In the last 3 years alone, astronomers have discovered an extraordinary number of planets that break the rules so completely, so specifically, and so repeatedly that the question is no longer whether our models of planet formation are wrong. The question is how wrong they are, and what they have been hiding from us about the universe we thought we understood. Stay with me, because what follows is not a list of strange discoveries. It is a systematic dismantling, one planet at a time, of the framework scientists have used for decades to explain how worlds are born. To understand why any of these planets are impossible, you need to understand what that framework actually says. The standard model of planet formation begins with a rotating disk of gas and dust surrounding a newborn star. Gravity gradually pulls material together into clumps. Clumps collide and merge into larger bodies. Rocky cores form close to the star, where temperatures are high, because lighter volatile compounds cannot condense their gas, and ice giants form further out, beyond what astronomers call the snow line, where it is cold enough for volatile compounds to freeze and contribute to the growing mass of a planetary embryo. The entire system ends up roughly sorted by size and composition. Rocky planets near the star, giant planets far out. Everything spinning in the same direction as the star itself, because everything formed from the same rotating disk. This model is elegant, it is mathematically consistent, it matches our own solar system almost perfectly, and it is being broken, case by case, by telescopes that keep finding worlds that did not read the rules before they formed. In June of 2025, astronomers announced the discovery of a planet called TOI 6894b, and the moment they published the measurements, the planet formation community had a problem. TOI 6894b is orbiting a red dwarf star. That in itself is not unusual. Red dwarfs are the most common type of star in our galaxy, and thousands of planets have been found around them. What is unusual is the size of this particular planet relative to the size of its host star. TOI 6894b is almost as large as Jupiter, and its star is approximately 20% the size of our Sun. To put that in terms you can picture, Jupiter orbiting our Sun is roughly equivalent to a pea orbiting a grapefruit. TOI 6894b, orbiting its star, is equivalent to a pea orbiting a lemon. The current best model of planet formation says that small red dwarf stars cannot produce giant planets, because the protoplanetary disk surrounding such a small star simply does not contain enough raw material. The disk is too thin, too light, too limited to accumulate the mass required for a Jupiter-sized world to coalesce. Researchers who announced the discovery acknowledged this directly. TOI 6894b is a record breaker. Its star is the smallest ever confirmed to host a giant planet, and right now, nobody has a satisfying explanation for how it got there. But TOI 6894b at least exists in a configuration where the planet and the star occupy their own separate domains. The system discovered and published in May of 2026 breaks things in a different and arguably more disturbing way. The star is called TOI 1130. It hosts a hot Jupiter, a gas giant roughly the size of Jupiter, orbiting so close to its star that its year lasts only 8 Earth days. Hot Jupiters are already strange enough on their own. They form far from their stars, and then migrate inward through mechanisms that took decades to work out. But here is the rule that astronomers attached to hot Jupiters once they understood that migration. On the way inward, the massive planet's gravity disrupts and destroys anything smaller sharing the inner region of the system. Hot Jupiters are lonely because they make themselves lonely. They scatter smaller planets into oblivion as they migrate. So when another MIT-led team used the James Webb Space Telescope to study the TOI 1130 system and found a mini Neptune orbiting even closer to the star than the hot Jupiter, completing its orbit in just 4 Earth days, inside the hot Jupiter's orbit, the reaction from lead researcher Chelsea Huang was exactly what you would expect from someone who has just found something that breaks a rule, she teaches. She said hot Jupiters are lonely. They are so massive, and their gravity is so strong, that whatever is inside their orbit just gets scattered away. But somehow, with this hot Jupiter, an inner companion has survived. The mini Neptune should have been destroyed millions or billions of years ago. It was not, and the James Webb data showing its atmospheric chemistry has now confirmed it is genuinely there, which means the destruction model that every astronomer accepted was incomplete in ways nobody predicted. In the same month, May of 2026, a completely different type of impossibility was confirmed in a system called LHS 1903. The star is a small red dwarf. Researchers identified 4 planets orbiting it, and on the surface, that sounds unremarkable until you look at which planets ended up where. In our solar system, and in the standard formation model, the pattern is rocky planets near the star, gas giants further out. This is not arbitrary. It is a direct consequence of the temperature gradient across the protoplanetary disk. Close to the star, Only rock and metal can survive the heat. Farther out, lighter elements and ices can condense and contribute to growing planetary masses. The LHS 1903 system looks like this in the middle. 2 gaseous planets in intermediate orbits, but the innermost planet is rocky, which fits the model, and the outermost planet is also rocky, which absolutely does not. A rocky planet in the outer orbit of a planetary system, beyond 2 gas giants, should not be able to form there under any version of the standard model. The team that confirmed it at the University of Warwick investigated every alternative explanation and found them all inadequate. What they were left with was a proposal called inside-out planet formation, an idea that had existed only in theory for about a decade with almost no observational support, suggesting that the planets in this system may have formed one after another at different times rather than simultaneously from a single protoplanetary disk, each under different conditions than the others. The outer rocky planet, under this hypothesis, may have formed under conditions so different from its neighbors that it essentially belongs to a different chapter of this system's history. It is the first observational evidence that strongly supports this idea, and it raises the question of how many other planetary systems we have catalogued are concealing a similar history that our models were never designed to look for. Now move from systems that break the rules of formation to a planet that broke the most fundamental rule of survival. The planet orbits a star designated 8 Ursae Minoris, roughly 530 light-years from Earth. The star is a red giant, a dying star in the final stages of its life, swollen to an enormous size as it exhausts its nuclear fuel. The physics of stellar evolution is well established and precise. Models show that this star, during its expansion phase, grew outward to roughly 0.7 astronomical units from its center. That is about 3/4 of the distance from the Earth to our Sun. The planet orbiting it sits at approximately 0.5 astronomical units, comfortably inside the boundary of where the expanding star should have reached during its giant phase. By everything astronomers know about what happens when a star expands past a planet's orbit, that planet should have been engulfed, torn apart by tidal forces, and consumed. The star then contracted back to its current size, and the planet is still there, orbiting normally, in a stable, nearly circular orbit, as though the star simply decided not to destroy it. The lead researcher on the discovery paper proposed 2 alternative explanations. Either the planet somehow survived a stellar merger event that altered the star's evolution before it could fully engulf the planet's orbit, or the planet is entirely new, having formed from debris ejected by the merger of 2 earlier stars. Both scenarios require a cosmic sequence of events, so specific and so unlikely that the planet's existence sits at the edge of what models can plausibly explain. NASA's official statement on the discovery was unusually direct. It said the discovery shows that planet formation and destruction are likely far more intricate and unpredictable than many scientists might have thought. But here is a category of impossible planet that has been accumulating for years and that breaks something more fundamental than any formation model. It breaks a rule of physics so basic that finding an exception to it required astronomers to double and triple check their instruments before publishing. Planets form from a rotating disk surrounding a rotating star. Because they form from the same material rotating in the same direction, every planet in a solar system should orbit in the same direction as the star's own rotation. This is not a preference. It is a consequence of angular momentum conservation, one of the most robust principles in all of physics. And yet astronomers have now confirmed multiple hot Jupiters orbiting their stars in retrograde, meaning they orbit in the opposite direction to the star's spin. The first confirmed case emerged in 2009 and was treated as an extraordinary anomaly. By now, researchers have found that nearly half of all hot Jupiters in certain surveys show some degree of orbital misalignment, and a significant fraction are in full retrograde. Simulations show that extreme gravitational interactions with companion bodies can flip a planet's orbit over very long timescales. But the sheer proportion of retrograde hot Jupiters suggests that whatever is causing this happens far more commonly than any model originally predicted, which means either the models of what companion bodies do to planetary orbits are significantly wrong, or something else is flipping these planets that nobody has fully characterized yet. And then there is a world that is not surviving at all. It is actively coming apart. Designated BDO 548668AB. Discovered in February of 2025, this rocky planet orbits so close to its star that the surface temperature has crossed the threshold where rock itself becomes unstable, not melts, vaporizes. The planet is losing mass continuously, with rock being converted directly to gas and forming a comet-like tail that trails behind the world as it orbits. It is the 4th disintegrating planet ever found, but the first discovered around this type of star, which means it is revealing a new context in which this process can occur. In some number of years, a timeline that depends on the rate of mass loss, this planet will cease to exist as a solid body. Astronomy has captured it mid-description, a world that has already crossed the boundary between planet and former planet, visible only because it is still in the process of becoming nothing. What all of these systems share, beyond the immediate strangeness of each individual case, is something more important. They share the property of having been missed by the frameworks that were supposed to predict them. The standard model of planet formation is not a rough sketch. It is built from decades of observation, theoretical refinement, and computational modeling at the highest level of scientific sophistication available, and these planets were not predicted by it. They exist in configurations the model says should not occur. Some of them require invoking processes, like inside-out sequential formation or late-stage post-merger planet coalescing, that had been theoretical proposals with minimal observational support before these discoveries confirmed them, and others like the mini-Neptunes surviving inside a hot Jupiter's orbit, or the retrograde gas giants that now constitute a near majority of their class, require revisions to the model's core assumptions that have not yet been fully worked out. Here is why that matters beyond the purely astronomical. Every assumption embedded in the search for habitable planets, for worlds that could support life, for targets of scientific interest in the coming decades of space exploration, is built on the same framework that these planets keep contradicting. If giant planets can form around stars too small to produce them, the distribution of giant planets across the galaxy is different from what we thought. If rocky planets can form in outer orbits beyond gas giants, the range of environments where life's raw materials might be available is different from what we thought. If planets can survive stellar engulfment and form from stellar mergers, the timeline across which habitable worlds can exist extends in ways the standard model does not account for. Each impossible planet is not just a scientific curiosity. It is a data point that shifts the picture of what the universe actually contains, and what it might be hiding in configurations nobody thought to look for because the models said they could not be there. The universe has been producing worlds without consulting our equations, and the most unsettling part of every impossible planet is not that it exists. It is the question of how many more like it we have been confidently ruling out, because we believed the model more than we believed the sky.